last talk, I would like to thank the organizers. We'd like to thank Alavo, Keith, and for very nice kind of invitation, allowing me to have this opportunity to go over my work in the last few years. And we're glad that my collaborators are here, so we continue to discuss and move the field forward. And so what we're going to talk about, the last talk will be some stuff about supercongruences. Here I start with some origins of supercongruences. In 80s, Beukers studied abelian numbers for the proof of both theta 2 and theta 3 being irrational. So one of the abelian sequence used to attain the famous proof that theta 3 is irrational is this one over here, which is written very explicitly in terms of binomial coefficients. For a natural number n over here, it's mentioned k from 0 to the subscript, and then there's a binomial coefficient, and n plus k choose k and square. You can write this down in terms of hypergeometric functions, which will be 4f3, and the parameters will be a negative integer, so it's terminating series, and then it's plus 1, n plus 1, n plus 1, and then the argument is 1 over here. And Fritz actually proved kind of a surprising kind of result. I make another typo over here. So what he proved is, if you look at what happens u to the m, I think I need to be careful what I try to say. Sorry, I think this could be -1 and -1 over here. So what he proved is very much like the Dwork's case, but the unit root is 1. So what he proved is very much like the Dwork's case with unit root 1. So the ratio here is becoming 1. And the key point will be now, instead of in the Dwork's result, that is modulo p to the r, it's modulo p to the 3r. The U function and its previous power in terms of p will agree modulo p to the 3r. So what he said himself is more or less he used a p-adic kind of analysis on the corresponding binomial coefficients. And meanwhile, he conjectured, if you look at, instead of right at p and negative p and 1 plus p, he look at half. So he go to, for any point which is bigger than 3, if you look at p minus 1 over 2 is integer, so this is a negative integer. If you pick the subscript to be p minus 1 over 2, you get a truncated hypergeometric series. Again, the argument is 1. For this particular truncated hypergeometric series, p-adically, it's congruent modulo p squared to 1/2, 1/2, 1/2, 1/2, and 1, 1, 1 down here. So he conjectured that this particular integer is going to be the same as, this is going to be a waveform modular form. And I think it's level A. AA is the same waveform modular form that I mentioned. It's the same as the p's coefficient, modulo p squared. And his conjecture was finally proved in 2000 by Scott Algren and Arnold, using Greene version of finite hypergeometric functions. And they further inspire Cuban's work for proving, removing all the p and do the truncation to p minus 1, they will agree even modulo p to the 3 power. Okay? So this is one of the origins for so-called the supercongruence. Why it's super? Because the Dwork tells us modulo p is true from what I'm trying to convey to you, but modulo p squared is higher. It's more than what the Dwork or commutative formal group theory will tell you. So it's called a supercongruence. And there are other origins of supercongruence. So this is another type is relating to famous Ramanujan kind of formula for 1 over pi. And one of those formulas Ramanujan gave is of this form over here. It's very much like you have 1/2, 1/2, 1/2, three of them, 1, 1, but this time you are getting an additional term. So you have 7/6 and 1/6 down here. So on top of this rising factorial factor, there is an additional term coming in. And Ramanujan said that if you put in the argument to be 1/4, for example, what you will get is 4/pi. So it's a formula for 1/pi. So Chudnovsky brothers used this kind of formula. They were able to compute the digits for pi very efficiently. And in 90s, when Hamme made a few conjectures correspond to the picture of Ramanujan's type formulas for 1/pi. For instance, what he did was he tried out when p is bigger than 3, what happens when you do the truncation to p-1. So he conjectured that this truncation for the classical case is 4/pi. What when Hamme discovered it's going to be a power of p and with a sign. So this is the Legendre symbol. And modulo a very high power, which is p to the 4. And later, in around 2000, later, there are a lot of supercongruences conjectures and results made by residue-sum. And inspired by two papers, there was the time around 2009, there was the time I pregnant with my younger daughter, that are inspired by two papers, one by Dermot McCarthy, Robert Osborne, and the other one is my collaborator, Zudilin. For Wading's case, he used WZ method. He proved one of the Ramanujan type supercongruences, not this one. And then I picked this up and I proved this particular case by using what we call, later Rawi and I call p-adic perturbation method. And so Rawi and I kind of generalized or gave more like mathematical descriptions how things can be put together. But for this particular example, I use a formula of Gassel and Stanton. This is an evaluation formula, which is the value is not plus or minus 1, but 1/4. So they allow me to do the job. And our so-called p-adic perturbation method was adopted by my another collaborator, Hollis Risher. She was able to establish almost all the Van-Hand conjectures. And then our method also we happily seen adopted by other researchers as well. So there are other origins of supercongruences why they got so a lot of descriptions. The other reason is because Fernando Rodriguez-Villegas, he make a few conjectures. Supercongruences occur to hypergeometric Calabi-Yau manifolds, including elliptic curve, K3 surfaces, and Calabi-Yau threefolds. For the elliptic curve and K3 surfaces, they were established by Eric Mortensen. And for the Calabi-Yau threefold case, there are a few results. I mean, his particular conjecture is for all the prime number bigger than 5. And if you have a alpha that we mentioned, there are 14 cases for fix a choice of the alpha multiset. There is an explicit waveform modular form. If you look at the piece coefficient of this waveform modular form and look at the corresponding truncated hypergeometric series at p-1, they will agree modulo p to the 3. And this is a supercongruence because the Dwork plus Gauss couplets will tell us mod p, as what I actually showed you earlier. But modulo p to the 3 is 2 power higher. And there are 3 cases which have been done previously, one by Cuban that I mentioned earlier, another one by McCarthy for the Dwork printed case. And then there is Jenny Fuseli and McCarthy did another case based on Cuban's result. So what he done here is 1/2, 1/2. This is 1/5, 2/5. This is 1/2, 1/4 case. And together with Fontaine 2, Noriko-Yuri, and Wading-Zudilin, we were able to solve all cases. Basically, the idea, again, goes back to the p-adic perturbation method. I'm going to show you later, after we announce the result, Rodriguez-Villegas, they make new supercongruence conjectures in 2017 when we have this conference in the Matrix Institute in Australia. So let me explain the p-adic perturbation method. I made some pictures. I'm not very good at that, so I'm trying to explain what that is. Hopefully remember a little bit more out of these pictures I'm making. All right. So what's the p-adic perturbation method? I'm trying to think about what that is myself. So the goal for this method is to achieve the left-hand side. There is a truncated hypergeometric series. So basically the object is a star. It's a truncated hypergeometric series. As we have seen in the previous slides, they all have the common feature on the left-hand side. It's a truncated hypergeometric series. The right-hand side, okay, left-hand side agree to the right-hand side modular power p. Okay, so when I thought about it, how we approach things, then the first thing I will say that I would recommend is to find out what's the nature of the right-hand side. It's kind of funny that for the cases I have done, we actually starting from nature of the right-hand side. The nature of the right-hand side for the Ramanujan type supercongruences, it's a character times p, or it could be the value of a character sum of the AP's value of a modular form, or in the ordinary case, it could be the Dwork gamma function, unit root function. All right. So that means could it be a tree, or could be, I mean, this intend to be a tree, but I don't know how to draw a tree using LaTeX. So I use this one, or could it be a heart, etc. For example, suppose the right-hand side is a tree. All right. So what I would like to do, the second step is put the tree back into the forest. So this is supposed to be a forest. So I find a formula for your tree. So put that into the background. All right. And now once it's into the background, you find a formula. Once you find a formula, you start to peel off in the formula. You get to the kernel, which is the desired term, which is the truncated hypergeometric series, the kernel. And then very often there are arrow terms going around it. So the loops are supposed to be arrow terms. The first step, you remove the arrow terms, and then you get to this picture, and then you compare, and then you say, hey, this is your right-hand side, this is your left-hand side, they are the same. All right. So this is what I call the p-adic perturbation method. So let's see how to put that into action. All right. So I'm going to show you this case. This case has been done by Mortensen and Wading-Zudilin using a WZ, Wilford-Zalber method. To me, that's a very mysterious method, but here it is. So I'm going to look at this. This is the case if I want to use what I describe as the p-adic perturbation method. What we're going to do is I'm going to actually look at both hand sides. It's a truncated hypergeometric series, and then I know the argument is -1. I know that it's going to be 4f3. I know that it's going to be a lot of 1/2, 1/2, 1/2. And then this is 5/4, this is 1/4. All right, so this is the left-hand side. And then the right-hand side. Right-hand side, it's difficult to deal with. If it's purely plus minus p, it's going to be difficult. I don't know how to deal with that in general. So I start to look for my forest. All right. So these are my footprints. All right. So I look. Then I find my forest. All right. So what's the forest I identify? All right. So I find a formula. So this is what I want. And I find this formula. All right. It looks exactly what I want. And why? Because now I have -1. All right. I have 4f3. And then the other thing I would like to say is this guy, it's going to be what we call well post. That means I'm adding things up. It's going to be 3/4. 3/2. So this, if I'm going to put A to be 1/2, it's also well posed. And if I add things up, I also get 3/2. Okay? And what's even better is if I deformate my parameters p-adically very close to 1/2. So I put the first one to be 1/2, the second one to be 1/2 and p-adically perturb, and D to be 1/2 and p-adically perturb in the way that they will compromise. And fortunately, the right-hand side here, it's a gamma quotient. It's nothing but this term I want. So this is the forest. I put my tree inside, all right? So I put my tree inside this forest, which is its background. Okay, then immediately, then I get to, hey, if I put that in, this is the forest. I'm locating my tree p-adically. I already get to what I want. This is the left-hand side, and already modulo p squared. That means originally I need 2 layers of arrow turn. I already get rid of 1 layer already. So I only need to get rid of 1 more layer of arrow turn. All right. And how to get rid of 1 more layer of arrow turn, because the target will be, I want it to be modulo p to the q instead of modulo p squared. What I did was literally, I look again, right? So I look at the literature. I look again and see what I really want over here. And what did I look for? What I looked for was I want something which is terminating. So I keep that 1 minus p over 2. I keep the same term, 5/4, 1/4. And then I perturb things a little bit more to make it into a formal power series. So I adding variables, 1 minus x, 1 plus x, to here, 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 and here. So that still everything more or less modulo p is still well posed. All right, so adding things up still 3/2 modulo p. And then this is a formal power series. The major term will be modulo p the same, or the major term, if I do the expansion, it will be the same as what I want. Then I can put that things into arrow terms. So I keep my major term. And then I have this arrow term because of the construction. It's going to be even function in x. And if I can prove p divides a2, then I'm done. So I have my major term. I remove 1 layer of arrow term. So I look again for another forest. So that will actually tell me this term is divisible by p. And luckily, I find another one. So in this case, for S3, it's give me more or less in the formula. I should probably mention that in the formula here, I have 1, 2, 3 degree of freedom, which is actually very useful in general. And then I look for another formula, WIPO, now giving me more degree of freedom. So this is a degenerate case for the WIPO formula that I mentioned. So for this case, we do have more degree of freedom. And so I can specialize things in the way that I get out exactly what I want. So these are the terms I want. I also further specialize 2 more other parameters, so they actually compromise. Say this term and this term p-adically are the same. So modulo p, they disappear. The same thing for over here. So even though it's 6f5, modulo p, it dropped down to 4f3. And more importantly will be this coefficient to the front. This coefficient to the front will be p for everybody. So this guy is p-adically the same modulo p as what I want. And on the right-hand side, everybody carry a copy of p. So which allow me to prove that p divides a2. So we actually get the conclusion from mod p squared to p to the cube. All right. Any question for this kind of illustration, how things can be done? All right, this is just the beginning of how we put things up together. So let me make a few remarks. After the paper that I wrote this paper out, I noticed that the idea has been adopted kind of Of course, including myself, Ravi and I expanding the vessel a bit more, including the description of how you convert from a lot of cases, the right-hand side you might see, which is a gamma quotient. Let me see, where's that? Yeah, there are gamma quotients. A lot of cases you do see gamma quotients. So Ravi and I try to kind of break down how you get from gamma quotient to p-adic gamma quotients. And so the method worked pretty well for Ramanujan type supercongruences. That means when the right-hand side is either a p power with a character, or when the right-hand side is an algebraic number with a Cm background, so you can write things up in terms of p-adic gamma functions. So for instance, after Ravi and I kind of laid down more kind of groundwork, we did this case over here, which is with value -1/8. In the background, there is a case-free surface with generic pickup number 19. When we get to the fiber lambda equals to -1/8, it's a elliptic curve with pickup number 20. Sorry, case-free surface with pickup number 20. So it's 2 copies of Cn elliptic curve. So we did that when we do the truncation at p-1, and we proved this is a conjecture by Jonas Kibelbeck, right, which was another student of Winnie. And Jonas Kibelbeck kind of conjecture when p is going to be 1 mod 4, this truncation will agree with the right-hand side, which is obviously it's going to have a Cm background modulo p power 3. This is a very singular case because in the background case 3, the H2 for this particular motif is 101 over here. There's only 1 0 in the middle, but this is p to the 3. All right. And meanwhile, this method, I mean, I have been pretty fortunate that I had tried many cases. I always able to find the classical hypergeometric identity. So, but however, I do seriously know the method relies on, there is a forest that I can look for it. So it relies on existing identities. So it's actually harder if the right-hand side is not of those forms. It will be much harder. So I would like to say that there are new identities discovered by the WZ method. I know a lot of papers using that method. Zudilin is one expert on this method. To me, again, it's a very mysterious method. I'm going to mention to myself it's an easier way to use a residue-sum technique to create identities. That means our next job will be we are going to build a forest so that I can use it to do the p-adic deformation. Okay. So let me get back again. Actually, the main goal will be the main results of this paper. It's actually a very nice project. It's much nicer in a way that we put so much things together and everything worked out exactly well, right? So the major result I would like to say is this is a conjecture of Fernando Rodriguez-Villegas. If you're doing the truncated hypergeometric function, you look at for any of the 14 families, we have already using hypergeometric sum. We noticed that the character sum will be a waveform modular form, the p's power plus a power of p. So we've done that in the lecture 3. And now we're going to look at this conjecture, which says that if I do the truncation at p-1, the right-hand side is going to be the p's coefficient of a waveform modular form. The agreement will be modulo p to the 3. And now what I'm going to use is the p-adic perturbation method. And in this method over here, of course, I said that it has happened that I want to put the right-hand side into background, put into perspective. There are 2 ways we have done it in the paper. One way will be when p is ordinary, we can use the p-adic, the Dwork unit root, because they agree modulo p to the 3. They agree modulo p to the 3. This is the first method. So this is the tree. The first tree is the p-adic unit root. The second way, we could directly use this formula. If we directly use this formula, we have this HP function on the left-hand side. It's written very explicitly in terms of Gauss sums, and then we convert that into p-adic gamma functions. So there are two ways to do it. And the key point will be, we're going to put them into the major term and arrow terms and trying to eliminate their arrow term. Okay. So here is the method for the first approach when P is ordinary. We will need to go from the Dwork, which is a generic congruence, to supercongruence. And basically, it's based on, again, the properties of p-adic gamma function. If we're going to write down in our left-hand side, basically the coefficients using a lot of rising factorial over k factorial. And in this lemma, we basically write down Q of the major part and then Q of the p-adic part. And this rising factorial can be written very explicitly in terms of its R. R is going to be a number. In our case, it's going to be a p-adically invertible element. If we do put that into the left-hand side, it will be another convention I should explain will be k. It's an integer. It's a natural number. So a will be its first digit, and the remaining digit is combined together into BP. All right. So the lemma, the left-hand side, if I'm going to express the rising factorial, it's relating to its later digits with a dash operation, and then there will be gamma, p-adic gamma function into the picture, and then there might be an additional p term, depending on whether you get to the jump. The rising factorial, to start with, is p-adically invertible, but when you go further, you might hit a p power. You have to peel that off individually. So this is the spirit of the lemma. We decompose the rising factorial into the p-adic gamma part, another rising factorial for later digits. Possibly there are additional arrow term because of the jump up from slope 0 to slope 1. And the jump we describe exactly occurs to this point over here. For any integer before this value, it's going to be 0. Otherwise, it jumps up to p-adically jump up to slope 1. And because of this lemma, we get to this very useful key reduction formula. The key reduction formula says, now if I would really want to describe what happens, k is in terms of a plus bp. What if I want to peel off my first digit? If I do that, then what we get is the remaining digits shifted with a dash operation, and there will be possibly an arrow term due to this slope going up one step, and a combined p-adic gamma term here. That we know that for the combined gamma term, there is the p-adic kind of expansion. If you ignore the deformation, it's 1. So it starts with 1, and then there will be arrow term coming from the G1 and G2 terms, etc. Okay, so this is what we call the key reduction formula. And with the key reduction formula, then we can do the following. But firstly, we're going to use the Dwork. The Dwork will be using ratios of truncated hypergeometric functions. So for our notation, if I truncate it to p to the s minus 1, I put the subscript 2 here. And basically, the Dwork tells me if in the ordinary case, this truncation will approaching gamma alpha p. And especially when s is greater or equal than 3, they will agree modulo 3. Okay? What I want will be basically now the first truncation is already good enough. So it turns out we're going to prove the first result, which is stated that if I'm going to, instead of writing that as a ratio, I write it as a product, which is uniformly for all the prime, doesn't matter whether it's going to be ordinary or not. Okay? So now we're going to express the left-hand side. The left-hand side is going to be doing the subscript all the way go up to p to the s plus 1. So we decompose the first digit and the second digit. The first digit is going to be 0 to p minus 1. The second digit can go up all the way to p to the s minus 1. And once we write it down into this way, we use the key reduction formula. Use the key reduction formula, we see that this is the first term. So this is precisely f1 of alpha. This is the shifted. The later term shifted. So this is f of s minus 1 alpha. But there are arrow terms coming from the jump. The jump function is describing in this way. And then there are factors coming from the p-adic gamma function. Then we can do the analytic continuation. So using the key reduction formula, we decompose them into pieces. And putting together, I'm not going to go through all the technicalities. I want to show you what the onion will look like. Right? So putting together, then what we get to is, it's going to be the same as what I explained. This is f of s plus 1. This is f1. This is f of s. And then there is the gamma term coming from the jump. And then the gamma factor has been decomposed into G1 factors for the J term. And then there are G1, G2 factors for the second arrow term over here. And again, for the G1 term, they are going to relating to the harmonic sums, partial harmonic sums. All right, so with this decomposition, we compare to what we want. What we want will be f of x times f1, all right? So that means I'm going to take off this 1 here. Once I peel off 1, and then the a will disappear into this picture, what I want is I can take off these pieces. The remaining thing will be about b. And this is a polynomial. We recognize there's a polynomial in b for the arrow term. It's graded, it's a quadratic polynomial. There is a first coefficient, there is a second coefficient. All right. So this is the first coefficient, this is the second coefficient corresponding to the 2 layers of arrow terms. And what we want will be, we hope their value will be 0 modulo p to the cube. All right. It looks like kind of, now everything's very explicit. The only thing is, how can I eliminate the arrow terms? It turns out this is the method I learned from Wading. That he used that already before. It's called the residue-sum method. The residue-sum method itself is a very innocent method. So what it says is follows. Suppose you start with a rational function. So this is a rational function of t. Then you write in terms of the partial fraction decomposition. In the construction over here, there are poles order at most 2, all right, occurs at minus k, all right, where k's go from possibly 0 all the way to the superscript. So I decompose that into partial fraction form. To compute this coefficient over here, it's exactly what we expect to do. We multiply at the case term the corresponding value t plus I, and then plot t to be minus k. All right, we specialize and multiply t plus I squared to eliminate the corresponding pole and specialize. So we get to the coefficient. In this computation, you can try it out later, but this is very explicit. Turns out to be very much relating to what Beukers, A prime number zeta 3 terms, each of the summits. For B, you can do it in a similar method. And then what you do is you use what you have done before you take the derivative, you can come up with the value for B, all right? And it turns out you use A over here, which is this combination. And it also, you use harmonic sums, which is great because I do need harmonic sums to approximate my G1 functions. And for this particular case, it's very nice. What's the residue-sum method? It says, okay, if I'm going to compute all the residues at the finite pole, it will be negative, the residues at infinity. What's the residue at infinity? And if you look at degree of this rational function, the degree down here is 2n plus 2. The degree up here is 2n over here. So the residue at infinity is nothing but 0. And now you put together the individual residue at the finite pole, you get to this identity, all right? This identity can be approved in such a way that I have not seen that in the literature of, going through hypergeometric formulas. So I was very pleased to see, hey, this is the formula that I want. If I say want to deal with the case with R1, R2 to be 1/2, 1/2, this identity exactly tells me the first arrow term will be 0 mod p squared. So of course, we would like to eliminate 2 of the arrow terms. So then we carefully refine the rational function by putting a p-adic perturbation. So we use the corresponding, there are R1, R2. So we can put R1, R2, we call R3 to be 1 minus R1 and R4 to be 1 minus R2. So we carefully perturb the corresponding term in the construction, and then the AI, where to stop, will be more or less minus Rj, the first digit. We put things together, which is just modified rational function as what I had used before. And amazingly, when we use this one, simultaneously, we erase both of the arrow term, right? So we actually concluded for the ordinary case, the Rodriguez-Villegas conjecture is actually true. Right? So of course, if you go to the general case, you use character sum. I'm not going to kind of give you more technicality, but what you will need will be another identity. And another kind of identity compared to the previous one, let me show you over here. This is directly harmonic sum, harmonic sum, harmonic sum. If you use character sum approach, by default, you will need identity involving k to the front. Right? For instance, if you want to do with 1/2, 1/2 case, you will need an identity of this kind, which is exactly 0. This is actually first discovered, I think, Scott Algren and Carano with another collaborator and the help of machine. They use WZ method. They were very pleased to announce there is such identity, which allowed them to prove Beukers conjecture. And for us, it's more than just this one, because to us, the magic is I use the same kind of the rational function. What we did is we put a copy of t to the front. So now the degree down here, it's going to be 2p. Up here is going to be 2p minus 1. So the residue is 1. It's also kind of easy to compute. So we got such kind of identity directly. Plus a careful p-adic deformation. We eliminate the 2 arrow term for general case as well when we use, the forest, I put the right-hand side in 2, it will be the HP function. So I think with that said, we proved this conjecture of Rodriguez-Villegas. And when we make the announcement, they actually immediately trying to compute more cases, right? So I really want you to say what they actually kind of listed on this paper, posted after the matrix conference. So what they posted is, now if you have a hypergeometric motif for their notation, if you have a few AI values, AI all lies within the range of 0 and 1. And they want alpha to be defined over Q, just like the Dwork. They try the case with beta to be 1, 1, 1. And then the argument they did is plus minus 1. And then what they said is, now you're going to look at the corresponding kind of the motif and see how it decomposed. And so it says that if you let A to be the unique submotif of the hypergeometric motif corresponding to the data over here, and so because of the setup, it will always start with 1. And then you're going to check the hypergeometric motif where your truncated hypergeometric function corresponds to. You're going to see how many zeros they will get before you get to the next one. And the number of zeros in between more or less kind of determine what's the supercongruence when you want to kind of tell in terms of more philosophical or heuristic kind of answer what's the power, y3, y4 sometimes, etc. So they gave this is what they believe to be in terms of motif. This is what you should kind of think about. And so it also become a question because generically, if you try this out, the hypergeometric motif might be kind of linked together. So it's not easy. If you listed everything in this manner, the hypergeometric motif they have, the Hodge numbers are all consecutive. The question becomes when it will decompose into pieces, right? So how to find special hypergeometric motif so it decomposes, then you can fish out submotif with a lot of zeros in between. So then it ties back to the motivation of my paper with Winnie Lee and Fountain 2. So Whipple's formula in the background was trying to create hypergeometric motif, which is highly decomposable. So we're getting back to this picture again. In this picture, again, we created a hypergeometric motif. Again, there are 3 layers using Whipple's formula. Whipple's formula predicted the existence of this term. And the corresponding Hodge sequence is 0, 1, 0, 0, 1, 0. And 1, 0, 0, 0, 0, 1 here, and then 0, 0, 1, 0, 0, 0 for the last term. So there is a gap of 4 zeros in between, all right? So when we get to the corresponding kind of conjecture of Rodriguez-Villegas, the generic congruence is this one. This will hold for any lambda. When you specialize, just like what they did, if you put that into 1 over here, I know the motif decomposed with 4 zeros in the background, and the power indeed go up to 5, which is 1 plus 4, number of zeros in between. And then there is a correction due to the mean to be -1. And I think I repeat that here a second time, but this is what I want to say in the end. We are actually kind of figure out a way at least to construct more cases. And we listed the corresponding conjectures in this paper joined with Winnie Lee and Fountain. And in another paper in 2018, I listed also more supercongruence conjectures. So the takeaway for my 4 lectures will be hypergeometric functions have a lot of symmetries. We use many of them. They are compatible perspective. I do mention about the perspective over C and then over finite fields into Galois perspectives. And then you can think about the p-adic perspective. They actually kind of thread lines to each other. And they are really explicit and they can be explored theoretically and computationally. And I would like to thank everyone again. And I'd like to thank also Amber initiated the invitation to start with. Thank you.
Let's thank Ling for some awesome set of lectures.
Thank you for staying to the end. Thank you.